Evening, everyone. I hope you all are going through the theory lectures. So today we'll be discussing some problems related to the theory that we have been discussing in the class. I hope my screen is visible now. So this is our 10th tutorial session. Let's start with some true-false problems. State whether true or false. Question number 1. The space CCR, the space of all continuous functions with compact support, is contained in the space L1R. And this the inclusion map is continuous. So by continuity of inclusion map, we mean the identity map. Suppose if CCR is a subset of L1R, then we can obviously define the identity map from CCR to L1R. And if this map is continuous, then we say that the inclusion is continuous. So in order to see this continuity, we generally check, we generally see that if some sequence Fn converges to F in CCR, then we should have that Fn is converging to F in L1R as well. So if this holds, then we directly say that the inclusion is continuous. So let's see solution. Firstly, let us see whether it is contained in L1R or not. If suppose F is some function, continuous function with compact support, then F is continuous, clearly. And there exists some compact set in R. So in compact set in R, we mean the closed and bounded interval. So there exists some A and B in R such that our function F is 0 outside the closed interval. Now let's look at whether it is in L1 or not. So integration over R mod f dx. This is nothing but integration from a to b, because outside this the function is 0 dx mod s. Now since f is continuous, mod f is continuous, and we know that a continuous function is integrable on closed and bounded domain by the Riemann integrability. So this is finite, since mod f is continuous and the interval close AB is bounded. So by the property of Riemann integrals, this is finite. Therefore, this tells us that f belongs to L1R as well. Therefore, Now, since f belonging to CCR was arbitrary, we can say that CCR is contained in L1R. Next, we need to see whether this inclusion is continuous or not. So I'm claiming that this inclusion is not continuous. So in order to prove my claim, I need to provide some example. I need to show that there exists some sequence Fn in CCR such that Fn is converging to some F with sup norm, that is sup Fn minus F, sup norm goes to 0, but its L1 norm does not is not convergent, is not going to 0. Okay, so I'll give some example. You can say that Fn is not convergent to F in L. Okay. So consider a sequence of functions Fn such that, let me plot this function first. I'm taking the type of functions which has a constant value 1 from minus n to n. Then it's 0 from minus infinity to minus n plus 1 here, and from n plus 1 to infinity. And in between, this is a straight line. So here, this is 1 by n. So one can observe that as n becomes large, this becomes smaller and smaller and so on. So intuitively, we can see that such a sequence will converge to 0 at least pointwise. So let me formally define. Consider the sequence Fn from R to R, Fn x. This takes value 0 when x is strictly less than minus n plus 1. Then its value is x by n plus 1 plus 1 by n. You can see that this straight line, this is nothing but the equation of the straight line, because we have 2 points. This is minus n comma 1 by n, and this is uh, minus n minus 1 comma 0. Using these 2 points, we can find the equation of the line. Then it is equal to 1 by n in the closed interval minus n to n. That's the n. Then its value is 1 by n for x belonging to n to n. So minus n, and this is minus n to n. And after that, again, you can find the equation of this line. This will be minus x by n plus 1 by n, or x belonging to open n plus 1, away open n to n plus 1. And after that, it is 0. So we can directly see that pointwise the sequence converges to 0. Clearly, Fnx converges to 0 for every x in R. Now let's look at its uniform limit. Now Fn minus 0 sup norm. This is nothing but supremum mod Fnx. X is belonging to R. Now we can see that the supremum of function is f of n is nothing but 1 by n. So this is 1 by n, which is going to 0 as it tends to infinity. Therefore, Fn converges to 0 in CC. Now I am saying that this will serve as my example, contradicting example. In that case, this function, the sequence should not be converging to 0 in L1. So let us see how. But integration R mod Fn, this is equal to minus n plus 1 to n plus 1, because otherwise it's just 0 Fn. So I can, based on the splitwise definition of this function, I can split this integral. This is equal to minus n plus 1 to minus n x by n plus 1 by n dx plus minus n to n. This is just 1 by n. Then from n to n plus 1, this is minus x by n plus 1 by n dx. And yeah, after that it's 0. Now please evaluate this integral and let me know what is it. I'll wait for 2 to 3 minutes. Please integrate this and tell me what is the value of this integral mod Fn over R. So please evaluate this integral and tell me. This will come out to be equal to 2 plus 1 by n, which is obviously always greater than equal to 2 every n in I. This gives us that L1 norm of Fn minus 0, this is greater than equal to 2, which tells that this Fn can never converge to 0 in L1. This implies Fn is not converging to 0 in L1. But we already had that Fn converges to 0 in CCR. Therefore, this function, the sequence of function serves as a contradicting example, showing that this inclusion CCR into the space L1R is not continuous. Therefore, Fn is a sequence in CCR such that Fn is converging to 0 in CCR, but Fn can never converge to 0 in L1R. Therefore, the inclusion map from CCR to L1R is not continuous. Hence, our given statement is false. I hope this is fine. Okay, let's move to next question. Question number 2. It says that there exists a function phi. There exists a function phi in L infinity R phi non-zero such that integration over R phi g is equal to 0 for every g in CCR. We need to check whether the statement is true or false. So we'll start with assuming that suppose such a function exists, and let's see if we get some contradiction or the things go well. Solution. Let if possible there exists some phi in L infinity R, phi non-zero, such that integration over R phi g is equal to 0 for every g in CCR. Now now since L infinity is the dual space of L1 and CCR is dense in L1R, we can see that this would eventually imply that phi should be 0. Let's see how. Now let f belonging to L1R be some arbitrary function. Arbitrary. Since CCR is dense in L1R, we can find some sequence Fn in CCR such that this Fn converges to F in L1 norm. This implies phi Fn converges to phi F for every, this is capital phi, for every phi belonging to the dual space of L1. And we know that this is equal to L infinity. Also, since if I define phi from L1R to R, phi F is equal to integration over R small phi, the one that we have assumed to satisfy the condition. This phi, capital phi, belongs to L1 star, because again, since this phi is in L, small phi is in L infinity, this will eventually turn out to be a bounded linear functional. This implies we must have integration over R phi Fn converges to integration R phi F. Now, since each of this Fn is a function in CCR, therefore, by our assumption, this integral should be equal to 0. Now, since Fn belongs to CCR for every n, this implies by equation 1, integration over R phi fn should be equal to 0 for every n in n. And this implies that integral r phi f, okay, is equal to 0 by second. Now, since this f was an arbitrary function in L1R, therefore we get, therefore integral r phi f is equal to 0 for every f in L1. And we know that if this happens, then our function phi should be trivially zero function, which is a which gives us a contradiction, because we had already assumed that this function phi is non-zero. Hence, our given statement is false. So the statement said that there exists some function phi in L infinity, and there exists some non-zero function in L infinity, such that integral phi f is phi g is 0 for every g in CCR. And using the fact that CCR is dense in L1R, and the dual space of L1R is L infinity, we've proved that if some function satisfies the condition that integration over r phi g is 0 for every g, then that phi must be 0. That gave us a contradiction, and hence the given statement is false. Please go through the solution. If you have any doubt, please let me know. So if not, let's move to next question. It says that there exists some function phi in L infinity star in the dual space of L infinity, such that satisfies similar kind of conditions as we did in previous problem. It's just that instead of L1, now we are in L infinity. So there, there exists a function phi, which is an L infinite in the dual space of L infinity, which is non-zero. There exists a non-zero function in the dual space of L infinity, such that phi g is equal to 0 for every g in CCR. Now, since the closure of CCR is the space C naught R, the space of all functions vanishing at infinity, which is a closed proper subspace of L infinity R. So we can find, so if we have the zero functional, so if I define a functional from C naught to C naught to R, which is zero function on C naught. Now, since C naught is a closed proper subspace of L infinity R, so I can extend it using the Hen-Banach extension theorem. I can extend it on L infinity. So I'll get a functional which is defined on L infinity and which has same values on the space C naught R, which was actually zero. So let's write it formally. How this happens. We know that in L infinity R, the closure of CCR is C. This is the space of all functions, space of all functions vanishing at infinity. And this space C naught R is closed proper subspace space of L infinity R if psi is the zero function on C naught R. G is equal to 0 for every G in C naught R. Now, since the C naught R is closed proper subspace of L infinity, I can find I can find a Hen-Banach extension for the functional xi. This implies there exists xi tilde from C L infinity R to R such that xi tilde restricted to C naught is xi. This xi tilde is nothing but the Hen-Banach extension of so this implies xi tilde g is equal to xi g for every g belonging to CCR, which is obviously a subset of C naught R. And which is equal to 0. Therefore, we can find now this xi tilde will act, will serve as our phi because this xi tilde need not be 0. Xi tilde is not trivially 0. Taking phi to be this xi tilde, we get phi non-zero and phi g is equal to 0 for every g in CCR. Therefore, the given statement is true. I hope this solution is fine. If you have any doubt, please let me know. All we had used is the fact that, yeah, mainly we have used the Hen-Banach extension theorem, and since C naught R is a closed proper subspace of L infinity R, so we could find its extension. Yes. Okay, let's move to next question. It says that C101, a space of all continuously differentiable function, that means their first derivative is continuous as well, defined on closed interval 0 to 1, is dense in LP01 for every p between 1 and infinity. Now, we know that CC01 is dense in LP. And by Weierstrass theorem, we can see that the space of polynomials, or we can say that for every continuous function, there exists a sequence of polynomials that converges to that sequence, that continuous function. Using this, we can see that the for any f in LP, I can find a sequence of polynomials that is converging to that f in LP space. And since the polynomials are continuously differentiable, so I'll get a sequence and hence I can show that C101 is dense in LP. So that is the main idea how we'll be proving that C1 is dense in LP. So the main thing is the Weierstrass theorem and the fact that CC01 is dense in LP. Let F belonging to LP01 be arbitrary. Since CC01 is dense in LP, that means its closure is equal to LP01, I can find a sequence Fn in this space of continuous functions with compact support defined on closed interval 0 to 1, such that the sequence Fn converges to F in LP norm. In LP0. Now, since Fn is a function with continuous function with compact support, it's continuous for every n in n. This implies by Weierstrass theorem for each n in n, there exists a sequence p n k of polynomials such that this Pnk converges to Fn n as k tends to infinity. And this is in space C01, that is with sup norm. So this implies we have the pointwise convergence for every x in 01 and Pnk. So now if I take its, this implies modulus Pnkx to the power p, this will also converge to fn to the power p x for every x in 0 to 1. So we'll be mainly will be using the dominated convergence theorem to show that Pnk converges to Fn in LP norm. And Pnk. So this is P corresponding to LP, and this P is the polynomial. Please don't get confused. P to the power P. Now this is less than equal to the sup norm of Pnk to the power P. And since Pnk is a convergent sequence in C01, therefore the sup norm is bounded. This is less than equal to m. Some m that will obviously depend on n, but independent of k, because this convergence is as k tends to infinity to the power p. Now this all obviously belongs to this space L1 because this is nothing but just constant. Therefore, by dominated convergence theorem, integral 0 to 1 mod p and kx to the power p, this converges to integral 0 to 1. No, okay. So this will converge to mod. This is mod fn to the power. Therefore, we get p and k converges to Fn as k tends to infinity in LP01 for every n in n. Now, if I define for every n in n, we define the sequence Gn to be P in n, then similarly you can see that this Gn will converge to F in LP01. And since this Gn is the sequence of polynomials, therefore, since Gn is, so I can directly write Gn belongs to C101 for every n in n. Why? Because Gn is a polynomial. We know that polynomials are continuously differentiable. It's polynomial. Hence, we got a sequence Gn in C01 such that Gn is converging to F in LP0. And since F belonging to LP01 was arbitrary, like that, C101 is dense in LP. Hence, the given statement is true. Please go through the proof once again. If you have any doubt at any step, please let me know. I can explain it again. Please Okay, if there is no doubt, we can move to next question. Number 5. It says that there exists a function g in L101. There exists a function g belonging to the space L101 such that integration 0 to 1 g phi dx is equal to phi at 1 by 2 for every phi in 16 0. Now, if I define a sequence of functions that is somehow converging to single point, something like this. Eventually, the sequence is such that it is non-zero in just a small neighborhood of 1 by 2. So eventually, the neighborhood is converging to 0. So if we integrate such function from 0 to 1, so we are mainly integrating just on the small neighborhood of 0.1 by 2, which will eventually go to 0. So in that case, the sequence of the integral g phi n, that would be going to 0. But again, we can see that at each point the function has a constant value. So this is just a trick. I'll try to find a sequence that has some constant value at 1 by 2, but its support is uh, uh, the measure of that support, or we can say that the interval is getting smaller and smaller. So in that case, we will get a contradiction because this integral would be converging to 0, but the value at 1 by 2 is constant throughout the sequence. So in that case, we get a contradicting example. So we'll be proving that the statement is false. Let me write it formally. Suppose phi n is a sequence in CC0 to 1 such that, so I want the sequence to be, suppose this is equal to 1 at 1 by 2. So all the terms should be 1 at 1 by 2, or all the functions. All the functions. Then I want its support to be going to 0. So it is 0 before and after some point. I take this to be 1 by 2 minus 1 by n. This is 1 by 2 plus 1 by n, obviously for every n strictly greater than 2. So we can see that as n tends to infinity, the support is uh, clearly the support of this phi n would be 1 by 2 minus 1 by n to 1 by 2 plus 1 by n. And as n tends to infinity, this is converging to a singleton point. Let me write this function formally. Um, in that case, such that, yeah, you can write its formal expression, how this function will be defined, uh, because that expression is not that important. But yeah, of course, while in order to learn the things, you should write that explicitly, how this function will be defined. So the main thing is that for any g in L1 0 to 1, the integral 0 to 1 g phi n. This will be obviously because phi n is 0 in these intervals. So this is 1 by 2 minus 1 by n to 1 by 2 plus 1 by n g phi. And here also, the value of phi n, this is less than equal to 1. So I can write it as less than equal to 1 by 2. Now this is an integrable function. No, we don't know whether this is integrable or not. Now this is less than equal to every function, every real number is less than equal to its modulus. So I can write it as less than equal to dx. Now since g is in L1, we know that mod g is integrable. This is an integrable function and we are integrating it on some e n g. Now since measure of the set en, this is nothing but measure of the closed interval 1 by 2 minus 1 by n to 1 by 2 plus 1 by n, which is just 2 by n. This goes to 0 as n tends to infinity. We know that if we are integrating an integrable function on a set whose measure is going to 0, so that integral eventually goes to 0. So this implies integral en goes to 0 as n tends to infinity. And this implies integration 0 to 1 g phi n. This is going to 0 as n tends to infinity. Now, if this g was the function that was satisfying our condition star, because even this g was also in L1. Na? So, suppose g belonging to L1, 0 to 1, is such that it satisfies star. In that case, integration 0 to 1 g phi n would be phi n at 1 by 2. And we know that phi n at 1 by 2 is 1 for every n as n tends to infinity. But by equation 1, we know that integral 0 to 1 g phi n, this goes to 0 as n tends to infinity. Now this gives us a contradiction. And hence, by contradiction, the statement star does not hold. Therefore, our given statement was false. I hope this solution is fine. If you have any doubt, please let me know. Please try to write how this function can be written explicitly. Now, this is nothing but just a straight line joining these 2 points. This point is 1 by 2 comma 1, and these are 1 by 2 minus 1 by n comma 0. This is 1 by 2 plus 1 by n comma 0. Just straight line joining 2 points. Okay, if we don't have any doubt, we can move to next question. So now we are done with true false. Answer the following. This is our question number 6. Let 1 less than p less than infinity define an operator A from domain of A, which is a subset of LP01 to the space LP01, where domain of A is a set of all functions f in LP01 such that there there exists a unique. So in order to represent this, we write it like this. There exists a unique G in LP01 such that integration 0 to 1 f phi dash, this is equal to minus integration 0 to 1 g phi dx for every phi n cc infinity 0 to 1. So this is how we are defining domain of our operator A. This is a very important operator. This will be useful if you are planning to study higher in this field. And for every f in dA, we define the operator A f mapped to this unique G. Now, since f is in dA, a domain of A, we will obviously have a unique G in LP that is satisfying these conditions. So the operator A maps this f to that unique G. So that this A is densely defined. This is an unbounded operator and a closed map. Okay, so we can get it as unbounded, unbounded, and closed operator. So we need to show these three things. So we, in order to show this, we should be aware of these terms. What do we mean by these? So what do we mean by densely defined? So densely defined now, because A was defined on dA, which was a subset of LP to LP. If I can define this operator on whole space LP. If for every f in LP, we can define A such that AF, this is equal to some limit AFN, where each Fn is a domain, and how this AFN is defined for every n, and then for every f in LP we define this as this limit. So we can do this only if so we can do this if our domain A closure, its domain of A is dense in LP. Because see, if domain A closure is LP, then for any f in LP, I can find a sequence Fn, which is Fn in dA, which is converging to this f in LP. So I can define A to be limit n tending to infinity AFN. because each AFN is well defined. Okay. Now, what do you mean by this unbounded operator? Unbounded operator is such. So we know that bounded operator maps bounded sets to bounded set. So if there exists a bounded set S subset of domain of A such that A S is an unbounded set in LP, then we say that our operator is unbounded. Next comes the closed operator. So when we are working on subspaces, so our A is defined in A, which is a subset of LP to LP. We say that A is a closed operator if whenever X F n is converging to F in LP with, see, we have sequence Fn is in domain of A. It is converging to some F in LP in the main superset. And also we have AFN converging to some other function G in LP. Now, if this hypothesis implies that AF is equal to G, in that case, we say that A is closed. I hope you all must have done all these things in the theory class, and this was just I was just recalling the things. So these three things we need to show. So let's start with the first part. Firstly, we'll show that DA closure, the closure of our so our domain set is actually dense in LP. Show that DA closure, DA is dense in LP. Clearly, since DA is a subset of LP, so its closure is a subset of its closure, and since LP is a closed, in fact, it's a Banach space, so this is equal to LP. Therefore, we have DA closure is a subset of LP. Now let F be a function in LP 0 to 1. So we have seen earlier in question number 4 that we have seen earlier about in question number 4 that the 1, 0, 1 is dense in LP01. This implies there exists a sequence Fn in C01 such that this Fn converges to F in LP0. Now I'll show that this this sequence Fn belongs to DA as well. Now if this is in DA, so we can say that we got a sequence in DA which is converging to F in LP. Therefore, DA is dense in LP. Now let phi belonging to CC. We need CC infinity. No? CC infinity goes 0 to 1. Be arbitrary. So this implies. So for in order to prove that this phi n is in dA, we need to show that integration 0 to 1 phi n fn phi dash is equal to some minus 0 to 1 some g times phi. So we'll be mainly using the integration by parts to show this. Now this is equal to, so let's use the integration by parts. It says that this is equal to fn as it is. Integration of phi dash is phi 0 to 1 minus integration 0 to 1 derivative of phi n, sorry, derivative of fn times phi. Now, since phi is in CC infinity, so it should be a 0 on the boundaries. So to have a compact support inside the closed interval 0 to 1, it must be 0 on the boundaries. So this gives us 0, 0 to 1, fn dash phi. Since phi belongs to CC infinity 0 to 1, should be 0 on the. So taking Gn to be equal to fn dash. Now, since fn is a function in C1, so its derivative is continuous. Therefore, Gn is a continuous function. And hence, so we want this Gn to be LP. Now, we know that a continuous function defined on bounded domain is integrable. So, and we have 0 to 1. If n phi dash is equal to minus 0 to Gn phi. Now, since phi was an arbitrary element in CC infinity, so I can write it for every CC, phi CC infinity close interval 0 to 1. This implies this Fn belongs to CC infinity. Sorry, Fn belongs to a domain dA for every n. Hence, we got a sequence Fn in dA. We know that this F, we already know that this Fn converges to F in LP such that Fn is convergent to F in LP01. Therefore, dA closure is equal to F. Hence, we this operator A is densely defined. Hence, A is densely defined. So first part is done. If you have any doubt, please let me know. All we need to show is that every function in LP, for every function in LP, we can find a sequence in our domain. And that sequence was constructed using the fact that C101 is dense in LP. And we used integration methods. So next we need to show that our operator A is unbounded operator. So that for that we'll look at a sequence such that a sequence will show that there exists a sequence Fn in dA, which for which the function the sequence AFN is an unbounded sequence. to show that this A is an unbounded operator. That means there exists a sequence Fn in dA such that Fn is bounded, but An is to infinity, or it diverges, or it is unbounded. Consider the sequence Fn defined as Fn t is equal to t to the power n for every t in closed interval 0 to 1. Now, firstly, let's see whether this sequence is a sequence in dA. Now, in fact, this is in C1, so we have seen above. Because since Fn belongs to C1 0 to 1 for every n, then as done above in first part, we can see that this sequence Fn is a subset of D. Now, this is a sequence in dA. Let's look at its LP norm. We need to show that this is a bounded sequence in D. So it's LP norm. P, this is equation 0 to 1. So Fn is t to the power n to the power p. This is, and just integrate it and you get 1. So now obviously this is always less than equal to 1. But agree n equal to 1. Therefore, this Fn is a bounded sequence in input 0. Now let's see. Now above we had seen that this, yeah, this Fn belongs to dA, and moreover AFN, this is Gn, which is Fn dash. So from here, and for every n, AFN, this is nothing but Fn ka derivative. You can write it as AFN at n point t. This is Fn dash at t, which is n times t to the power n. Now look at the LP norm of AFN. This is 0 to 1. What is AFN? AFN is Fn dash, which is n t to the power n minus 1 to the power p dt. Now this is equal to n to the power p, and p n, sorry, p n n to the power n 0 to 1. So this is n to the power p p minus 1 by p. Now for all p strictly greater than 1, this goes to infinity. Therefore, we got a bounded sequence whose image is diverging to infinity. Hence, this operator is unbounded. Okay, so this is 0 to 1 n to the power p t to the power p n minus p. So this will be n to the power p to the power n p minus p plus 1 0 to 1 by this is p n minus 1 plus 1. This is n to the power p like p n minus 1 plus 1. This is always greater than or equal to n to the power p by p n minus 1 because p n minus 1 plus 1 is greater than or equal to since 1 is strictly less than p. So we get p n minus 1 plus 1. This is strictly less than p n minus 1 plus p, which is np. This implies 1 upon p n minus 1 plus 1. This is strictly greater than 5. This is strictly greater than 1 upon n. So this is n to the power p minus 1 and p. And this goes to infinity as n tends to infinity because p is strictly positive, strictly greater than 1. So therefore, we got the bounded sequence for which whose image is diverging. Therefore, this operator is unbounded. I hope this solution is fine. Please go through the solution. I'll wait for 2-3 minutes. If you have any doubt, please let me know. Otherwise, then we'll move to its part 3, where we'll be showing that this map is a closed map. Okay, now let's show that this map is a closed map. Closed operator. That is, if Fn is a sequence in DA such that Fn converges to some F in LP and AFN converges to some G in LP, then this G should be equal to A. Condition. Let Fn be a sequence in DA such that this Fn is converging to some F in LP01 and AFN is converging to some G in LP01. We claim that G is equal to AFN. Now, sorry, G is equal to A. For any phi in CC infinity 0 to 1, integration 0 to 1 Fn phi dash, this is equal to minus 0 to 1 AFN phi. This is nothing but just the definition of the operator F. Now we'll be taking limit on both sides. So here, see that AFN, this is converging to G in LP, and this phi belongs to CC infinity, which is a subset of LP dash 0 to 1, where you know that P dash is such that 1 by P plus 1 by P dash is equal to 1. So basically this phi is in the dual. So by continuity of the bounded linear functional, we'll get that integration 0 to 1 phi AFN converges to 0 to 1 phi G. Similarly, here since Fn converges to F in LP 0 1 and phi dash. Now since phi is in CC infinity, so it's smooth, all of its derivatives are continuous, and hence phi dash, its all derivatives will also be continuous and with compact support. So phi dash will also belong to CC infinity 0 to 1, which is again a subset of LP dash 0 to 1, which is the dual space of LP. This implies, and hence by continuity of any bounded linear functional, phi 0 to 1 phi dash Fn, this should converge to 0 to 1 phi. Therefore, taking n tending to infinity in first, you get the left hand side is nothing but integration 0 to 1 phi f dx. This is equal to minus integration 0 to 1. This is phi g1 g. And this is the definition of our operator. This implies that this G is equal to A. That is what we needed to prove. Therefore, A is a closed I hope this is fine. We have mainly used the fact that phi is in CC unity and hence in all length. Next, we'll be showing that this DA, this domain of A, actually forms a Banach space. We can define a norm on this set, this subset of L. Uh, let's see. Seven, one less than two less than infinity. A is the operator defined in A01, in A01, and it will be as defined above. In fact, we can take this P to be less than greater than equal to 1. It's just that for P equals to 1, we don't know whether it is unbounded or not. That's not required. We defined as in question number 6. Set this space, set space H equals to dA with its norm into LP norm of F plus LP norm of A. Show that H is a Banach space. And the inclusion map H subset of LP01 is a continuous linear map. Inclusion of H in LP01 is a continuous linear. Firstly, let's start with showing that this H is a Banach space. Clearly, you can see the check yourself. This is a non-linear space. We'll prove that this is a Banach space. That means every Cauchy sequence is convergent. So let's start with a Cauchy sequence in H. Show H is a Banach. That means every Cauchy sequence converges in H. Let Fn be a Cauchy sequence in H. This implies Fn minus Fn for H norm goes to 0 as n tends to infinity. This implies Fn minus n Lp norm power p. This is less than equal to, obviously, by the definition of norm in H, this is less than equal to Fn minus Fn H power p. Now this is going to 0 as n tends to infinity. Similarly, AFN minus AFN less than equal to Fn minus Fn H power p plus n tends to infinity. So this implies Fn and AFN are Cauchy sequences in LP. Fn and AFN are So this one comes because of uh, this comes because of the linearity of A. You can see that yourself. Fn and AFN are Cauchy in LP 0. Now, since LP01 is a Banach space, there exists some F and G in LP01 such that this Fn converges to F in LP01 and AFN converges to G again in LP01. And since this map A is a closed operator, as we have proved above, since A is a closed operator, we get G is equal to AF. Now this implies F is in dA, which is H, and now Fn minus F H to the power B is equal to Fn minus F in power B plus AFN minus AF B power B. This is nothing but, now since this AF is G, minus F B plus AFN minus G. Now this goes to 0 as n tends to infinity because Fn converges to F and Gn converges to G in LP. So this goes to 0. Therefore, Fn converges to F in H. Now, since Fn was an arbitrary Cauchy sequence, therefore every Cauchy sequence in H converges to is convergent in H. Hence, H is a Banach space. Next, we need to show that this inclusion map is continuous. That means the identity map defined from H to LP is continuous. That means whenever we have convergence in H, we must have convergence in LP. That is, I think we can directly see that because of the definition of the norm in H, we can directly show that this inclusion map is continuous. So the main important thing here was the fact that this operator A is closed. That helped us to prove that the limit will be in H only, and hence that is a Banach space. So second part, we need to show that the identity map from H to LP01 is continuous. Let Fn converges to F in H. This implies the LP norm Fn minus Fp minus P. This is obviously less than equal to Fn minus F HP. Now, since Fn is converging to F in H, this goes to 0 as n tends to infinity. This implies Fn goes to F in LP as well. Therefore, the inclusion map is continuous. I hope this is fine with everyone. You can go through the proof once again. If you have any doubt, please let me know. After that, we'll move to the last question of this session. Okay, if there is no doubt, we can move to next question. Question number 8. Let 1 less than equal to p less than infinity. Let H be the space as defined in question number 7 above. H be the space as defined in question number 7. Okay. Show that H is isometrically isomorphic to a closed subspace of LP01 cross LP01. So this is a subspace of a product space. Show that H is isometrically isomorphic to a closed subspace of LP01 cross LP0. Part B says that deduce that H is separable H is separable and it is reflexive for 1 strictly less than p less than solution. So we need to show that H is isometrically isomorphic to a closed subspace. That means we should be able to find some operator, some a bounded linear operator from H to some S, which is a subset of LP01 cross LP01. Now, this should be isomorphic and isometric. That means norm DF should be equal to norm DF in this LP cross LP. This should be equal to norm F in H. This T should be bijective. In that case, we can say that, and moreover, this H should be a closed subset of LP01 plus 0, LP01. And if I define T from H to LP01 is LP01 as T of F is equal to F comma T. This is the tuple. This implies the norm LP cross LP norm. Now we know that this is defined as LP norm of first component plus the second component to the power by p. And this is the definition of our norm in H. This is FH. Therefore, this T is an isometry. Is an isometry. This implies T. Okay. And if F1 and F2 are such that Tf1 is equal to Tf2, in that case we get F1 of A1. This is equal to, this is just the definition of the operator T. And by equating component wise, we get F1 equals to F2, and this gives us that this T is injective. And we know that if any injective map defined from its domain to range is bijective. Therefore, T from H to range T, this is an isometric isomorphism. So, metric, or we can write it as isometry, is bijective isometry. Is a bijective isometry. So all we need to show that, or all we need to show is that this range T is closed. So let F Fn be a sequence in range T such that Fn converges to some Fn. This range T was a sorry, this range T is a subset of NP cross NP. So this is a tuple. This is also for Fn Gn is a sequence in range T such that the sequence converges to some F comma G in LP01 cross LP01. Now, if this FG is in range T, then we get that range T is closed and hence we are done. So, this implies 0 is equal to limit n tending to infinity. The H norm of Fn Gn minus Fg to the power P. This is equal to limit n tending to infinity Fn minus F P norm plus Gn minus G P infinity. Now, since this Fn and Gn are in range space, that means Fn comma Gn is something of the form Fn comma AFN. That is how our range space is defined. Any element in the range space is actually T of something. No? So we can write it as this T of Fn. So this is actually limit n tending to infinity norm Fn minus F AP plus A Fn minus G P. So from here, we get that Fn converges to F in LP01. Obviously, because this LP norm is lesser than equal to the this quantity, and which is converging to 0. And AFN is converging to G in LP01 again by closed, since since A is closed operator, we get G is equal to AF. This implies F comma G, which is equal to F comma AF. This belongs to range space of T. And hence range T is closed. Therefore, we are done. That is what we needed to show them. Uh, Therefore, this H is isometrically isomorphic to a space, a set range T, which is a closed subset of, which is a closed subspace, because of always range set is a subspace. Range T is therefore H is isometrically isomorphic to a closed subspace of LP cross LP. That is what we needed to prove. Next, we need to show that H is separable and reflexive. That comes from the fact that LP cross LP is separable and reflexive. So directly, since LP01 plus LP01 is separable for every one less than equal to p less than infinity. So it's every closed subspace will also be also separable for every p between 1 and infinity, which is now since range t is isometrically isomorphic to this range t. So this implies H is also separable for every p between 0 and infinity. Similarly, since LP01 cross LP01 is reflexive, this is for p strictly greater than 1. We get again its closed subspace will be reflexive, and hence H is reflexive for every one strictly less than 2. I hope this solution is fine with everyone. If you have any doubt, please let me know. I can explain it again. Please, if you have any doubt, you can ask. Okay, then, if there is no doubt, we can end the session here. We'll meet next Friday and discuss some practice problems. I hope the session was fine with everyone. You were able to understand whatever I was explaining. At least I tried my best. And yes, if you have any doubt, you can ask me anytime. Okay, then, thank you.